Welcome to week 3, Regression and ANOVA. The course will begin to be a little more difficult this week and the next week, so make sure you're paying close attention to the text and be sure to email me with questions if you have them. You can also consult other web-based resources for help too. So last week we talked about correlation. Regression is similar to correlation in some ways, but it's also different. The correlation coefficient told us the degree of relationship between two variables, if we remember back. When the correlation coefficient, if it's positive, it tells us that when x goes up, y goes up, and if it's negative, x goes up and y goes down. Regression, on the other hand, allows us to assess the degree of the relationship, and we also can make predictions about the possible values of a variable. So correlation said, okay, well, when y is up, when x is up, y also tends to be up. But with regression, we can actually get a very specific value for how much y will go up when x goes up. Regression is always conducted with continuous data. However, you can convert non-continuous data to continuous data using dummy variables. I won't get into the specifics of dummy variable coding. It's described in the book, and it may be on your exam. But for all intents and purposes, just know that regression is computed with continuous data. We may the dummy variables may be on the exam, but I probably won't make you get into the specifics of it, and maybe just ask you what they are. Regression, ANOVA, and many other statistics are all different cases of linear models. In other words, we are using lines to summarize, describe, and predict data. The lines we use to predict data come from the same conceptual formula that you've seen multiple times now in the field text and in these slides. The formula y equals b0 plus b1 x1 plus e may seem familiar from elementary algebra. In fact, this equation can be rewritten into y equals mx plus b plus the error term at the end. Again, we're using a straight line to predict y values. b0 is the intercept. Again, remember back in elementary algebra, the intercept is the value of y when x is 0. In the case of regression, b0 isn't always meaningful, it's just a prediction. For example, we can have an intercept of b0 for height, weight, or IQ, but talking about the value of y when height, weight, or IQ are 0 isn't very meaningful. What is 0 height? What does 0 weight mean? Again, it's a prediction. b1 is the regression coefficient. It tells us how much of an increase or decrease in y we can expect for 1 unit of x. For example, if the regression coefficient is 10, for every 1 unit of x, we can expect an increase in 10 units of y, plus some error. The regression coefficient is unstandardized and represents what y was measured in. So if it was money, for every unit of x that goes up, let's say you want to look at the regression between height and income. So for every inch in height you go up $10 in income. That's how you would interpret a regression coefficient of 10. One of the nice things about regression is you can calculate regression with multiple predictors. We couldn't do that with correlation, remember? With correlation, we just have a predictor variable and an outcome variable, just one predictor. With regression, you can use multiple predictor variables in the same equation here, this line here. You can just keep adding predictor variables indicated here by b of n. However, with enough regression coefficients, you will account for all the data. But at that point, you aren't really predicting anything. You're just describing the data you've collected. And in fact, as we'll see, the significance test for a regression model depends on how many predictors you used. If you used a lot of predictors, you kind of take a hit in terms of your ability to detect an effect, because you're kind of increasing the likelihood just by chance that you'll detect an effect by adding lots of predictors. So it's not always in your best interest to have too many predictors. A few predictors are good, but you can definitely have too many predictors. So how do we find the line that best fits the data, the regression line? The line that best describes the data is called the line of best fit. It's also called a regression line. If you remember back to an earlier lecture, the fit of our models can be determined with the least squares approach. The line of best fit is the line that minimizes the vertical distances here between the observed y. How many units in y is the line? How many units in y is the observed y from the predicted y? We take the vertical distance. The line of best fit is the line that minimizes the vertical distance between the predicted y's and the observed y values. Put another way, the line of best fit minimizes residuals. Residuals are the differences between the predicted y's and the observed y's. Now, we could test all the possible lines and find out which one fits best, but luckily, some advanced calculus is able to find the line for us pretty quickly. If you really want to know how that works, there are videos online, or you can take a multivariable calculus course, and if you do, I'll wish you good luck if you decide to do that. We're not going to talk about it in this course. We're not going to go over the calculus, the multidimensional calculus, and I wouldn't know about it anyways. Because the residuals lie on both sides of the lines of best fit, of the line of best fit, some residuals will be positive, some will be negative. And overall, if we sum all those residuals, they should pretty much be zero. They should be right around zero. So we square the residuals prior to summing them, and these squared residuals are used to assess the fit and predictive power of our model. When we calculate the significance of our regression line, or the line of best fit, we are comparing the sum of squared residuals for the regression line to the sum of squared residuals for the mean. We are asking, in other words, does the line of best fit do a better job predicting scores than the mean? Does the line of best fit reduce the sum of squared residuals more than the mean? The cartoon in the bottom right demonstrates this. I'll zoom in a little bit. You can see the sum of squared residuals for the mean. This is the mean, the brown line here. And the sum of squared residuals for the regression. So the sum of squared residuals for the mean are in brown. They're these brown boxes because they're squared. The sum of squared residuals for the regression are in red. When there's no relationship between x and y, the sum of squared residuals is approximately the same for both the mean and the regression line. In other words, the regression line approximates the mean when there's no relationship. Now I'm going to break here, and I'll ask you to watch videos 1 and 2. They're from this guy named Salman Khan. They're posted to D2L, and they have some extra info about the line of best fit and regression. Salman Khan is an excellent teacher. He has lots of videos on different topics as well as self-tests on khanacademy.org. You can take those tests to test your knowledge on a topic. It's totally free. I like him because I think he's he's an excellent teacher. He explains things in a very clear and easy to understand way. And again, there are lots of different topics there on his webpage, not just statistics, but he has other topics that he teaches, mostly in the realm of kind of science and mathematics, but he has some other topics that he teaches as well. So go ahead and take a look at videos 1 and 2. I think one video is about 8 minutes and the other is about 10. And then come back and watch part 2 of this video series that I'm talking